So I want to wrap up today with a little bit of a lighter assignment. And even though it's going to be this is one of those kinds of assignments where you could get a group of second or third graders to sit down and play around with it, and they could probably get something out of it. And so I want us to have that kind of fun, but I also want us to be thinking about what that fun is pointing towards. And this is an activity where, in coloring the arcs of a diagram on a knot, we will hope to learn something about the structure of that knot. And in particular, if we can agree for today, we'll be able to prove this later, but we'll agree for today that how we color a knot is an invariant of the knot. How we color a diagram, is an invariant of the knot. Then how we color a diagram can actually be a way of telling two different knots apart from one another. What I mean by that is that when I have a knot invariant, it will have the property of what I call discrimination. A knot invariant can tell two different knots apart from one another. Because if I can show that a certain property holds for one diagram but does not hold for another diagram, if that property is an invariant for knots, then that property either has to hold for all diagrams of the same knot or for no diagrams of the same knot. And so as soon as I have a disagreement in an invariant, then I know that those two diagrams must represent different knots. We call that the property of discrimination. So for our activity today, we're going to be discovering whether or not a diagram can be colored using three colors on its arcs. So for today, red, green, and blue will be the three diagram colors that we'll use. And we'll have to set down some rules for what it means to color a diagram. We can't just put the colors on however we want to. We want there to be some kind of structure to it. But if we can show that one diagram can be three-colored, tricolored, and another diagram cannot, then if tricoloration is a knot invariant, it must mean that those two diagrams cannot represent the same knot underneath. So that's the property of discrimination. Every kind of invariant that we discover for knots is going to have that discrimination property. If we can find a disagreement between two diagrams, we know that those two diagrams represent different knots. What's unfortunate is that most invariants don't have the confirmation property. If the property holds for two different diagrams and is true for both, or is false for both, if we get agreement, it's usually not enough to say that those two diagrams are diagrams of the same knot. So invariants are really good at telling different knots apart, but most invariants are not perfect in telling two agreement diagrams, telling two of the same knots, two diagrams of the same knot, as diagrams of the same knot. So let's look at what is the definition for tricoloration. What are the rules of the game for coloring the arcs of a diagram? And then we'll give you some practice in actually applying it to do some discrimination between different diagrams of knots. Is that a three coloring of a knot diagram is just a way of assigning to each arc in the diagram one of the colors, red, green, or blue. We'll just use those as our three colors today. But not all ways of doing that will be what we call a valid according to the rules of our coloration game. Not every one of those colorations will be valid. In order for a coloration to be valid, we need at every crossing for either all of the three arcs at that crossing to have the same color. So I have, for example, so this crossing right here on my screen is an example of a crossing where all three of the incident arcs at that crossing have the same color. This piece is colored red. This over piece, like the bridge over here, is colored red. And then this other piece underneath the bridge here is colored red. So this is a meeting of red, red, and red together. And so that would be an example of a valid crossing in this scheme. So that's one possibility, is that we have three arcs of the same color meeting at a crossing. The other possibility is that all three of the arcs that meet at that crossing have three different colors. And so let me see if I can find an example of that. Actually, it looks like I don't have an example of that on my screen over here. So sometimes it's easier to think about what's not valid. And what's not valid in a coloration is a situation where two of my arcs that are incident at a common crossing have a given color, and the third arc has a different color than that. Right? So this crossing right here, say, this would be an invalid coloration because I have a blue, my overstrand here is blue, but the other two are the same color that's different from blue. I have two reds coming in here. I can't have two reds in a valid coloration at a crossing unless the third crossing is also red and all three of the colors match. Okay? So those are the rules. Either all of the colors have to match at a crossing, or all three of the colors have to be different that are coming into that crossing. And that's it. It bears mention, too, that we can mix and match these two different types of crossings within a given diagram. So not every crossing has to be all three the same, or not every crossing has to be all three are different. We can have some crossings be three of the same. We can have other crossings be all three different, as long as every crossing is one of those or the other. Does that make sense? And if such a coloration exists for my diagram, then we call that diagram tricolorable. There's just one eventuality that we need to rule out. We need to rule out this coloration, the coloration where we just assign the same color to everything. We're not that interested in that kind of coloration because any knot diagram can be colored all with the same color, and that would be de facto valid coloration, right? Because all three colors at each of these crossings is the same. So I could just color the whole thing red and call myself done, but that's not very interesting. I could color the whole diagram green, and that's not interesting either, even though it's a valid coloration. So in order to really be tricolorable, we want there to be a non-trivial three coloration, a way of using more than just one color to create a diagram in which those crossing rules hold. So I can't just change one of my arcs because here I have an invalid crossing, right? Because I have two that are the same green, but the third one is not. All right, so that's an invalid crossing, and so my coloration is not valid. So to fix that, I should pick one of my other arcs and maybe change it. Well, if I change it to blue, then I'm again going to have a problem with this crossing right here, where I have two blues but not a third. So to fix that, maybe I change this arc again and make it red. And now I have a valid tricoloration because at every one of my crossings, we either have all three colors the same, which doesn't happen in any of these crossings, but it could, right? Or the other possibility, all three colors are different. And indeed, at this crossing, all three of the colors are different, a red, green, and a blue all coming together. The same is true at this crossing, the same is true at that crossing. So we would call this knot diagram tricolorable or three-colorable, because we can come up with a way of using more than one color to color the arcs and still have at each crossing either all three colors are the same or all three colors are different. If we agree that coloration, tricoloration, is an invariant of knots, then it will have the discrimination property. If one diagram can be tricolored and the other one cannot, then we know that those two diagrams must represent different knots, distinct knots. We can't have two diagrams of the same knot if one of them has this property and the other one doesn't, if this property is an invariant for knots. So your job between now and the end of our session together today is to figure out whether this diagram, and I haven't told you what knot this diagram represents, but the question I'm kind of asking is, could this be a diagram of that same K32, that same knot that we diagrammed up here? Could this potentially be the same knot as this? One way of answering that question is to apply those rules for diagrams, the Reidemeister moves, to see if we can turn one diagram into another. But as I mentioned before, that's a really hard problem in general, to figure out whether we can twist and do like do-si-dos and stuff to turn one diagram into another. And so we're always looking for these smarter ways of telling when two diagrams might represent different knots. And the way we're talking about now is, can we three-color this diagram? If the answer is no, then because we could three-color this diagram, those two diagrams must represent different knots. Problem 5, same question, different diagram. Can I put a three-coloration on this diagram? If I can't, then it must be different than this one. If I can, then what? Okay, so that's kind of the piece that I want to leave hanging out there. So when we get a no answer, when we get a disagreement, we know for sure we have two different knots. When we get an agreement, two diagrams that both have the same invariant property, we don't necessarily know whether we have the same knot, so we might need to do something else to determine whether those two diagrams really represent the same thing. So that's the goal, parts 4 and 5 on this activity for today, and then between now and when we meet again, try and make some headway on the other problems on this second one of our activities.